Dongjie Tang. Today, we will share a topic called gRemote, API Forwarding Powered Cloud Rendering. With the popularity of the gRemote in the cloud computing, how to increase its utilization rate becomes a hot topic. To achieve this purpose, many technologies appear, and we will classify them into three categories, as shown in the following slides. Traditional GPU virtualization, thin client framework, and the remote API forwarding architectures. Furthermore, we will see the limitations of these frameworks and why we need to propose a gRemote. The traditional GPU virtualizations, taking a virtual machine as an isolation unit and share multiple VMs among the same hardware resources, is widely adopted in many hardware vendors, including Intel and NVIDIA vGrid. Thin client techniques, attributing all workloads to the server side, and taking the client side as a displayer only used to capture the user behaviors and represent the results, is widely used in cloud gaming frameworks, including the Google Stadia and the Microsoft xCloud. The remote API forwarding systems, the prototype of gRemote, allowing users to run applications on the hardware accelerators by remoting commands through the network, proposed by Akuda and implemented in the Amazon Elastic GPU. We can see that all three architectures have the same goals, improving GPU utilization rate, different from two previous architectures, taking the client as a displayer. The remote API forwarding architectures has the potential to fully utilize the client-side hardware resources, reducing resource waste to a great extent. Furthermore, remote API forwarding systems can increase the server utilizations within the cloud, because nowadays, many cloud vendors do not configure each server with a dedicated graphic card. For example, when a server with a dedicated GPU is fully connected, but its GPU still has most available resources, remote API forwarding systems can borrow some GPU resources to other servers to increase its utilization rate. Amazon Elastic GPU focuses on that. Even though remote API forwarding systems have many advantages, however, it still has one big limitation: shared resource interference. Due to the characteristics of GPU, cannot finish any task without help from the CPU. Its shared resource interference comes from two aspects: GPU risk caused by the GPU overuse, and the CPU risk caused by the CPU shortage. The following two experiments show the results. We conducted the experiments on two machines: GPU server with NVIDIA GeForce 1060 and the gRemote client without any dedicated graphic card. The first image presents the GPU utilization, and the second shows the performance of different number of applications. We can see that without any isolation method, all the benchmarks, micro or macro, take the nearly 100% of GPU resources. And when a new application comes, as shown in the image 2, it causes a great performance degradations due to its resource robbery. For example, we can see that GILs lose more than 70%. Thus, when the resources are sufficient, there are still some performance interference happened. Later, we will see why CPU shortage happens theoretically and practically. As we said before, GPU cannot finish any rendering task without the help from the CPU due to the lack of interfaces with operating systems and some I/O devices. For the execution steps of each rendering application, except for the pipeline created and the GPU rendering, the remaining tasks belong to CPU. Just from the number of workloads, CPU needs to handle more jobs than GPU. As shown in the experiments, when two machines are connected, when CPU becomes fully utilized, the GPU rates becomes lower. These behaviors will hurt the performance of applications and cause performance degradation. Based on these issues, we propose our own design, gRemote, API forwarding powered cloud rendering, focusing on minimizing shared resource interferences from two aspects: improving CPU resources and containerizing GPU usage for each application. This is a detailed framework of gRemote. The entire framework resides in the application layer, transparent to users and independent from the hardware configurations. The whole entire framework can be classified into two parts: computing parts, also called the client side, focusing on CPU workloads, and the rendering part, also called the server side, focusing on GPU workloads. So far, gRemote supports two transmission protocols, Ethernet and RDMA. Compared to the conventional remote API forwarding architectures, gRemote innovates three units: command buffer to store intercepted commands for further processing, library stub to minimize CPU pressure on the server side, and the GPU throttle to limit GPU usage of each application. On the client side, after API router, there are still many CPU workloads left, including the context establishment, display settings within a command buffer. In addition, there is another issue that the CPU commands and the GPU commands are mixed together. Thus, library stub will go further step to leave some more workloads to the client side. The library stub has two functions: command reorganizing and workload split. Since CPU and GPU commands are mixed together, library stub needs to reorganize the order of APIs. Instead of sending all commands to the server, gRemote only sends the established context and the GPU workloads to the client side. Thus, gRemote improves the CPU resources from only the server side to both the server and the client side. On the rendering side, gRemote put forward GPU throttle to containerize each instances within a specific GPU resource. As we discussed before, only two functions belong to GPU workloads: pipeline creation and pipeline rendering. The speed mismatch between these two workloads makes GPU use more cores to cover until the entire chip is fully utilized. Thus, based on saving CPU resources, gRemote regulates frame creation speed to limit each application within a certain GPU usage. When the server is fully utilized, response value sets to 0 to notify the client side to wait for other applications. Now we will see the evaluation of the gRemote performance. The entire evaluation has two parts: the performance application after optimizing shared resource interference, and the hardware usage for each application after optimizations. Before we show the results, we will talk about the experiment setup. The entire systems operate on two machines, one configured as a GPU server with one NVIDIA 1060 and Intel Core i5. The other one configured as a gRemote client only with Intel Core i5. To make sure the comprehensiveness and fairness of the whole evaluation, we take the two baselines: gRemote base, a traditional remote API forwarding system without any optimizations, including GPU throttle and CPU resource improvement. Amazon Elastic GPU, a closed-source and state-of-the-art commercial product, which has similar targets with gRemote. Due to the closed source of Amazon Elastic GPU, we take the FPS of every single application as 100% and normalize the remaining values based on this FPS of the same application. For gRemote base and Amazon Elastic GPU, the performance degradation happened when a new application comes. For gRemote, the line is quite smooth and no obvious variations appear. And we can see that there is one exception, that draw elements, whose FPS is controlled by time. Thus, gRemote did nothing to this application. This is the server-side hardware usage of each application. Due to the closed source of Amazon Elastic GPU, we cannot obtain any server-side information. Since we offload some CPU workloads to the client side, we mitigate CPU pressure by more than 50%. For different requirements of GPU throttle can also relate different size of usage for various applications. Since the gRemote incorporates network transmission function into the entire system, we should optimize transmission protocol to lower transmitted latency and reduce the network bandwidth consumption as our future work. This is our conclusion. Compared to traditional remote API forwarding system, gRemote optimizes shared resource interference from two aspects: to mitigate the CPU resource bottleneck and also to isolate the usage for GPU usage for each application. And this is our talk. Thank you very much for your time. And any questions?